Hi, thanks for joining me today. I've got a fun little video planned. It's all to do with the summation of finite series. I've written down some facts on the board and then I'll get on to today's problem. So these are the two main facts I'm going to be using today. Firstly, the sum from k equals 1 to n of k is n plus 1 over 2. This is really standard whenever you're introduced to summations or perhaps proof by inductions. This is one of the first things you'll see. You can prove it by induction, you can prove it sort of by reversing the order. And in fact, I've proved this in a previous video using another method as well, a third method. So I'll leave a link to that in the description below. Also, another really cool formula is that the sum from k equals 1 to n of k cubed, so the sum of the first n cubed numbers, is equal to n squared times n plus 1 squared over 4, which just so happens to be this thing here squared. So the sum from k equals 1 to n of k all squared. Okay, so this is quite neat and quite cool. Whenever you're introduced to this, you go, that's a nice coincidence. And that's what the sort of the inspiration for the problem today. We have an, a sequence of positive real numbers, and it has the property that the sum from k equals 1 to n of ak cubed is the same as the sum from k equals 1 to n of ak all squared. We want to know how many such an are there. Now, of course, there's at least one, the case where an equals n, or ak equals k, because this is a fact, we already know it. We can prove this thing here by induction, both of these results. That's fine. But we want to know, are there any more? And if there are, how many more are there? Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself. And I'm going to get stuck into a solution. Okay, so the solution to this problem is that there's just one. So there's just one sequence of positive real numbers, an, with the property that whenever you take the sum from k equals 1 to n of ak cubed, that's going to give you the same thing as the sum from k equals 1 to n of ak all squared. And of course that 1 is going to be the case, or I claim that if this holds, then ak must equal k for all k. And I'm going to prove this, and thus we can then deduce that there must be only one sequence of real numbers, an, with this property. Okay, so I want to prove that ak equals k, and to do that I'm going to use induction. So let's look at the base case, k equals 1. Okay, so we want to prove that a1 equals 1. Well, so a1, well, that's precisely, well, let's start with a1 cubed, for example. a1 cubed is precisely the sum from k equals 1 to 1 of ak cubed. Okay, but a fact we know is this thing here. This thing here is precisely the sum from k equals 1 to 1 of ak all squared. But this thing here is nothing but a1, so this is just a1 all squared. Okay, so we get a1 cubed is equal to a1 squared. Now, because everything is positive, and in particular non-zero, I can divide through by a1 squared, and thus deduce that a1 equals 1. Okay, so that proves my base case. Now let's make an assumption. So let's suppose, and we're actually going to use strong induction, for some n, the sum from k equals 1 to, let's suppose ak equals k for all k in 1 to all the way up to some number n. And now we're going to look at the case n plus 1. So we want to now prove that an plus 1 is n plus 1. Okay, so now what we want to do is prove that an plus 1 is equal to n plus 1. And like with the base case, we're going to start off with the fact that we know this thing holds for all n, so it will hold for n plus 1. So let's write out the left-hand side. The sum from k equals 1 to n plus 1 of ak cubed is equal to the sum from k equals 1 to n of ak all squared. Oh, n plus 1, sorry. Okay, so this thing is a fact, and we're going to work from this thing down to try and derive that an plus 1 equals n plus 1. Well, this left-hand side here, I can write as, if I take out the last term, which is an plus 1 cubed, I can write this as an plus 1 cubed plus the sum from k equals 1 to n of ak cubed. Okay, so if I get rid of this last term, and then just shove it out the front here, so an plus 1 cubed plus this thing here is going to give me this thing here. But this thing inside the bracket, I can do a similar sort of thing. Write this as the sum from k equals 1 to n, and then add on my n plus 1th term. So I'm going to rewrite this thing here as my n plus 1th term, an plus 1, plus the sum from k equals 1 to n of ak. Okay, now when I expand the brackets on this right-hand side, I get an plus 1 squared plus 2an plus 1 times the sum from k equals 1 to n of k, ak, plus the sum from k equals 1 to n of ak all squared. Okay, so I get this formula here. Now firstly, I can cancel out this thing here with this thing here, because remember, a fact is that this thing here holds for all n. So the sum from k equals 1 to n of ak cubed is going to cancel with the sum from k equals 1 to n of ak all squared. So let's rub those two out. Okay, so things are getting a bit cleaner. So I get that an plus 1 cubed is equal to this thing here, an plus 1 squared, plus 2an plus 1 times this summation here. But remember, by our assumption, ak equals k for all k between 1, 2, 3, all the way up to n. So in particular, I can just swap out this ak here for k, because each of the sort of increments are numbers in this set here. Okay, but the sum from k equals 1 to n of just k is n plus 1 over 2. Remember, that was one of the facts I had written on the board at the start, and again, you can prove that by induction. And in fact, I've proved it in a previous video using quite a cool combinatorics proof. A link for that in the description below. Okay, but this thing here is nothing but n times n plus 1 over 2. Okay, so in fact, let's bring that down to this line here. And then divide by 2, but that will cancel with that 2 there. So it's plus an plus 1 times n plus 1. Okay, cool. Now we've got something that looks like a cubic in terms of an plus 1. But remember, an plus 1 is a positive real, and in particular it's non-zero, so I can divide through by an plus 1. So here I get an plus 1 squared. Here's just going to become a first power, and this one here is going to vanish. So I get an plus 1 squared equals an plus 1 plus n plus 1. Now it's a quadratic in terms of an plus 1, and we can solve these quite nicely. Let's bring everything onto one side first. Okay, and now remember, we want to show that an plus 1 equals n plus 1, so it would be really nice if n plus 1 was a root of this equation, and it's not too difficult to see that it is, and in fact you can factor this out nicely. This thing here factors to an plus 1 minus n plus 1 times an plus n. Okay, and just to see that, an plus 1, oh, that's supposed to be a plus 1 there. When you do the first two terms here, that's going to give you the an plus 1 squared there. Now an plus 1 times plus n, then times minus an plus 1 times n minus an. The n and the n are going to cancel, and you're just left with the minus an plus 1, which is that thing there. And then multiplying the constant terms together, you get minus n plus 1 times plus n, which is going to be minus n times n plus 1, which is that guy there. Okay, so you get this thing here equals 0. But remember, an plus 1 must be a positive number, so this factor here we can get rid of, because this would insinuate that an plus 1 equals minus n, which is obviously not true, because minus n is negative. So we can conclude that this guy here equals 0, and thus an plus 1 equals n plus 1. Okay, and that proves, or ends our proof by induction. Okay, so let's just quickly go back to our original problem, and I'll just talk about that for a second. Okay, so the original problem we had was we had a sequence of real numbers, an, where each of the an's are positive, with this property here that the sum from k equals 1 to n of ak cubed is equal to the sum from k equals 1 to n of ak all squared. And then we derive just using induction that means that ak must be equal to k for all natural numbers k. Okay, and the reason I think this is pretty cool is firstly this formula here is certainly unexpected. There's no natural reason why this should hold. There's no sort of intuitive reason why when you do the sum of the first k cubes you should get the sum of the first k numbers and then you square it all. It might just be a really nice coincidence, but what's even more impressive is that there's some sort of converse as well. In other words, if we have the sequence of numbers, then this thing here holds. Now I guess one sort of subtlety is the positiveness I used, and that was in particular, I used it twice. So firstly, when we're doing like our base cases and stuff, so we're not dividing by 0, because of course we could have the trivial sequence of 0. So if an equals 0, 0, 0, and so on, then that obviously satisfies this thing here. But that's a bit boring. We want some interesting ones. So that's why we had positive, but also the reason we had positive was, if you remember when we were factoring our thing here, we could have also had the an plus 1 equals minus n. And then we could get some other sequences as well if we if we change the word positive for non-zero. So I encourage you to have a look at that case as well. But I think this is quite cool when you just focus on positive reals, because you get a nice converse to this statement here. If you are new here, I hope you enjoyed the video. Please do consider checking out some of my other fun maths videos as well, and subscribing if you haven't already. Anyway, that's all for now, and I will catch you in the next one. Have a great day.